Last time we were working on section 2.6, related rates, and this is the section where we can actually take our implicit differentiation and put it to use inside of application problems. That's what this is. So we talked about the basic idea of doing this is that a sketch is almost always helpful, and so make sure to use those. And then setting up equations related to those sketches and to the relevant quantities that you're asked to find. Differentiating implicitly with respect to time. So not dy dx's, but dy dt's and dx dt's and d theta dt's or whatever you've got going on. Substituting in known quantities and then solving for the remaining rates. We had done a couple of examples. This one was one that involved a triangle. The triangle ones are sort of popular because they're familiar formulas for you. So you see questions about these with Pythagorean theorem all the time, or sine, cosine, tangent kind of relationships all the time. So you do have to be careful that you're looking at the relationship that they reference. So on this one, it talked about a fish being reeled in at a rate of 1 foot per second from a height that is 10 feet above the water. So we drew a height of 10 feet above our blue water below. And then it referenced the angle of elevation, theta, between the fishing line and the water. So that's why we actually put that in there. If it didn't reference an angle and it talked about the length of the, how far away from the dock or the boat or something like that the fish were, we would actually be using the water's length on the bottom, and we would be doing it like the water was flat, not wavy, the way I drew it. So it would really look more like a triangle. And then we'd probably be using the Pythagorean theorem to deal with it, right? Okay, so make sure that just because you see triangles doesn't necessarily mean you're dealing with angles. You might, but you might not. And then it talks about how quickly the rate that the angle of elevation is changing when there's a total of 25 feet of line. So one of the things that's a little bit tricky when you're looking at these problems is being careful on which quantities that you have numbers for that are constant and which ones are changing. So like I wrote in the 10, and I actually wrote it on the diagram as 10 feet, and I didn't ever give a variable name to that side of the triangle because it's not a variable. It is a constant. That's not changing. Okay, but the fishing line itself is changing its length. So when I did that one, I gave it a variable name, and I also wrote in that there's a 25 that's going to be there at some point. So at some point, that's going to be a length of 25. And then any of the relevant rates that it gives you, and it will often give you at least one rate. In fact, I think it might always give you at least one rate of how something's changing in order to find the other pieces. This one told you that the rate at which the fishing line is being pulled in, right, the guy's reeling the fishing line in, is 1 foot per second. And so the quantity that's asking you for is the rate that the angle's changing, which would be d theta, because that's the angle, dt, over time. And then the way that we take a look at this particular picture is we look at the ratios that we have. So on this one, the 10 is an opposite side to my angle, and then the x and the 25, eventually it'll be a 25, are the hypotenuse of my triangle. So we need the relationship that relates the opposite side and the hypotenuse, and that's where we got sine from. So we set up that the relationship was sine of theta equals 10, which is the opposite over the x. And then when we differentiated, we had the cosine of theta, d theta dt, and then 10 over x is the same as 10x to the negative 1. So I dealt with it just like a simple power rule instead of a chain rule, or instead of a quotient rule. And you bring your negative down, decrease your power by 1, so you have negative 10x to the negative 2, and then it's dx dt. Okay, every variable, when you take its derivative, you're going to get a d, the variable dt, on related rates every time. So this one gives you dx dt on the right. And then once you have it at that point, you're starting to plug in the values that you know. We actually know the value for x at a specific point. It was 25. We know the dx dt, it was negative 1. But we run into a kind of a problem. We don't actually know the angle theta, and we don't know the cosine of theta. So we can do that one of two ways. We can either find the angle theta, and that's what we actually did first, is we said, okay, if we find the angle theta, we could just do the inverse sine of 10 over 5. We already have the relationship sine of theta equals 10 over 25, and so we did the inverse, and so we found that the theta is, and I should have written approximately, but with 6 decimal places anyway, it was this 0.411517. The other thing that we could do is that we could take a look at what the cosine of that angle was, especially if you were working with something where you already had the Pythagorean theorem set up. That might make sense to look at something from the perspective of the three sides of the triangle. And so if you find that third side is A, then you could actually take a look at the quantity there from that perspective and solve it from there. So we didn't do that way, we just talked about it. and we ended up finding that theta is 0.4. Sorry, what was that?
Why did you use sine specifically?
For the measurements, because we had the opposite and the hypotenuse. And if you do like SOHCAHTOA, if you remember that, opposite and hypotenuse is sine. So we could, if they were asking about the angle of elevation changing between the fishing line and the guy's height, above the water, like his vertical distance. So if they referenced like this piece right here, then we would be, if that were our angle theta that we were referencing, then we would have used cosine. So you just have to use the sine or the cosine or tangent potentially if that were the one that you were wanting for your sides. Sometimes you see questions like this where like a ladder is sliding down a wall. That may be what's in your homework, I'm not sure. But that's like a classic one where the ladder is sliding down the wall. There's the fishing line one. There's ones that, images that create triangles are quite popular to create related rate questions about. I don't really know why that's the case, but you see a lot of related rate questions with triangles. So. The second one we did was a sphere, and the sphere was actually a really nice friendly one because it only had one variable and one relationship to really talk about, and it was the volume. So the volume was 4/3 pi r cubed. Just as a reminder, I talked to you guys about last time that if I use something that's not like a triangle, something that's not a square or a cube, something that you should know, right? I'll make sure and I'll give you some formulas. I think the volume of a sphere is probably not something that most of us just are going to have on the top of our memory right away. And so that's one that I wouldn't necessarily expect you to know. And so if I gave you something a little obscure, I would make sure you had a formula for using it. I will say I have done a question before where we talk about the volume of a box. I would think that you should know the volume of a box, length times width times height. It's not anything complicated, but every time I do that one, I have people look at me like I'm from Mars or something. So, there's, go back through some of them. I mean, if you just look at them, probably some of them will just stick in your mind. You'll be like, oh, yeah, I saw that one before. And so there's several in this section, like in your book, that you can look at the formulas they've used. And I think on the front and back of your textbook as well, like there's the appendices, that there's some volume diagrams in there that might be good just to glance through and reference. All right, we have one last question. And this one is about oil spilling out of a tanker. So oil spills out of a tanker at a rate of 90 gallons per minute. The oil spreads, we'll talk about the 90 gallons per minute in a minute. The oil spreads out in a circle with a thickness of 1/8 inch. Determine the rate at which the radius of the spill is increasing when the radius reaches 100 feet. Okay, so can you picture what's happening? Yeah, and so we're pouring something out, okay, whether it's the tanker or whether it's a cup of water. And what happens is it spreads out, right? And it spreads out in a circular pattern. And because it's oil, it's a uniform thickness, all right? Like it can't just evaporate into the ground like water would or something like that. This is oil. It has a thickness to it. So the image that we're getting looks like a circle, but it has a height. So what is an image that's a circle with a height? It's a cylinder, right? So we actually get a cylinder, and I will kind of exaggerate the height just so that we can draw a picture that's a little bit more helpful to work with, but it looks something like this. We've got this very thin cylinder. So at some point in here, we are going to need a formula about cylinders. Is the formula about cylinders going to be volume or surface area or area? What are we going to be doing with this? It's be a volume, right? Because it's the volume that's spilling out. So we are going to need a volume formula for the cylinder. The volume for a cylinder is actually pi r squared times h, like that. Okay, so again, like that's one that you might remember that one, but it's really just not one we use all that frequently. I would give you that if you needed it. There's another weird thing there's a couple weird things going on in this problem. Somebody tell me something you feel like looks a little bit weird, and you're like, I'm not sure how to deal with that one.
90 gallons per minute.
Yeah, that 90 gallons per minute, that's the volume, right? But it's in gallons, and nothing else is given in gallons, right? Like when we looked at this circle over here, the sphere, we could talk about volume fairly easily because the units matched. It was all about centimeters cubed and centimeters, right? And gallons is definitely not a volume that matches inches or feet or anything like that in our problem. So that's another piece that I have to give you because it won't make sense otherwise. So let me give you the, well, what we just said here is that that's how the volume's changing. That's dV dt. It's 90 gallons. Was it per minute? Okay, 90 gallons per minute. And let me see where my piece is that I have to tell you. Here it is. 1 cubic foot is equal to 7.5 gallons. That's the relationship. I had to look that one up. I definitely don't know that one off the top of my head.
Is there going to be something like that on
I don't remember. I don't remember if there's one specifically with gallons. Mooney says no, since he's looked at it, so I'm going to guess he's right. If there were, what I did when I did this problem originally is that I just Googled how many feet are in a gallon or something like that, and then you can find it. It's pretty simple to find a relationship like that when you have the internet to access. There's something else in this problem that's a problem. Like we could change this now into cubic feet, right?
We don't know the radius.
Okay, we do know at some point, right? But it is changing, correct? So in terms of like a picture, the radius is definitely a quantity that is changing in this situation. But at some point, the radius is going to equal 100 feet. Okay, there's something else weird going on. There's something I haven't labeled. Let me start there. What have I still not labeled? The height. So this is my height, and what's my height? 1/8 of an inch. Does anybody see something we're going to have to deal with?
Inch to feet.
We've got inches and feet in the same problem, right? So we either need to turn everything into inches or we need to turn everything into feet.
Which one is better?
The values will look larger if we turn them into inches. Okay. The problem with turning into feet, not problem, but the thing to be aware of is that 1/8 of an inch is already a fraction of an inch. So it's going to be a very, very tiny number if we turn it into feet. Which one would you guys like to do?
Huge number.
You want to deal with big numbers or tiny numbers?
Big.
You want to say feet? All right, how about a show of hands? Who wants to change things into feet?
Everything else already have feet, so you only have to control them.
About half and half. Okay, fantastic. All right. So you want to change it into feet just because there's only one value in inches right now? Okay, that's fair enough. Is that okay with everybody?
Yeah.
Okay. All right, so we do need to still change this. When we said what the relationship is, we didn't actually change it. I'm not sure how much of conversion of units. Okay, that was not what I wanted to do. How much of conversion of units you've seen before, but you'll definitely see it at some point in chemistry if you haven't already. So we need the gallons to go away, and we need it to be feet cubed. So the relationship has to be set up something like this in a fractional way. So we have 7.5 gallons is 1 cubic feet, 1 cubic foot. So, yep, it is. So we're going to actually take 90 divided by 7.5. So what is 90 divided by 7.5? 12. Nice, a whole number 12? That's friendly, isn't it? Okay, 12 cubic feet per minute. And we need to turn this 1/8 of an inch into feet. So how are we going to do that?
5 by 12.
Right, it's 12 inches in 1 foot. So we're going to have to divide 1/8 by 12, or you could say that we're going to actually be multiplying 1 times 1 and 12 times 8. What's 12 times 8?
896.
96. This is 1/96 of a foot. Okay, so when we do in fact deal with height, we're going to put 1/96 in for h. And I don't want this to be labeled as h because it's constant, right? The thickness of the oil stays constant. It doesn't sort of melt into the ground and go away or something like that. It's not changing because it's not something like water. All right, so I think that we've got all of our relevant quantities. We've got dV/dt here. We've got our height right here. We've got our radius, which is changing. Okay, so we don't want to actually plug it in until the very end. But I think we've got all the quantities actually in the right units now. Does that look okay? Okay, so we've got a formula that says volume equals pi r squared h. And we're ready to take a derivative of this implicitly. So what's the derivative? I'm sorry, let me do one thing. The height, we actually know it's 1/8. I'm going to put it in, not 1/8, 1/96. I'm going to go ahead and put it in because it doesn't change. Okay, the v. What is the derivative of v? dV dt. All right, now we have pi r squared times 1 over 96. What's the derivative of that going to be? 2 pi r dr dt, right, times 1 over 96. Or, if you prefer, we can put the over 96 over here.
You could actually do like, you could multiply it with 2.
You can simplify it with the 2. We're going to plug the r radius in here in a minute anyway, so I'll just hold off on my simplifying for now. But is everybody okay to this point? Okay, I think that we have all the quantities that we need. dv dt, we actually know that quantity, right? What is it? Yeah, that was the 12. And you can put in the feet cubed per minute if you want. I usually leave the units out and put them back in at the end because they just kind of, they get a little bit messy in the middle. You do need to make sure that they match before you do that, but we already did that already. So the radius was 100 feet, and then I had 96 on the bottom. And then dr dt is exactly what I'm looking for, so I don't have a quantity for that one. I'm trying to find it. All right, so in terms of this particular formula, we're ending up with 12 times 96 divided by 200 pi
144 divided by 24.
is equal to dr dt. What did you get on what?
144 divided by 25.
You had 144
Divided by 25.
divided by 25 pi?
Yes.
Okay. And then let's get that as a decimal value. Okay, now I've got two very different
yeah,
answers.
oh.
And I don't have this one written down because I had done mine with inches on my paper, so let's double check.
Divided by pi. Yep. 1.8.
1.833 is what I have. Did you do the pi as well? Did you get the 1.83?
Yeah, I got the
I have an idea about what you guys are doing, but let me double check it. Yes. Okay, right now, what you guys are doing is not putting parentheses around what's in the denominator. So your calculator thinks that you want to do the division and then you want to multiply by pi. So, good to know.
So 1.8.
Yeah, 1.833. And I think what we had said when we were looking at this before is that we were going to go ahead and write down 4 decimal places within this particular section of material. So you just follow the directions for whatever it asks for on the paper, but or the problem. But this would be 1.8335 what? Close. Feet per minute. So why feet per minute instead of cubic feet per minute? Right. So the dRdt, the radius is in feet, and then the time is in minutes. So we've got feet per minute. Okay? That is our final answer. Now, what if they did this problem, and then they did a part B on there, and they said, what is that for in inches per minute, and what is it in feet per minute? Do you have to redo the whole problem?
No.
No. You would just multiply this by 12, right?
Yeah.
I mean, because that's you know, there's 12 inches in a foot, so that's what you would do. Okay, just checking to make sure. All right, everybody good with that?
Yeah.
Awesome.